The aim of this flying lesson is basically threefold. You'll learn how to fly a powered descent at a controlled angle and rate of descent, and also at a desired airspeed. You'll learn how to fly a glide descent with the throttle closed. And, as a descent is the flying maneuver which immediately precedes the landing, you'll also learn how to descend with flap, using power, in the approach configuration. In the briefing on climbing, we learned that if engine power or propeller thrust is in excess of that required for straight and level flight at a given airspeed, the aircraft will climb at a certain rate or angle of ascent. The reverse is also true. That is, if the pilot reduces the power setting below that required for straight and level flight at any given speed, the aircraft will descend at a given rate or angle of descent, respectively. The more the pilot reduces power and propeller thrust, the greater will be the rate and angle of descent for a given airspeed. Let's look at this situation more closely. Stating what may appear to be the obvious, we may say that if, for a given airspeed, say 100 knots, the thrust being developed by the propeller is equal to the thrust required for level flight at that speed, an aircraft will indeed fly level, and thus maintain its altitude. Here we see an aircraft in level flight, with the flight forces in equilibrium. In the picture, we have depicted all four principal forces acting through the centre of gravity, and have ignored the tailplane downforce. This is a simplification, but will serve for this explanation. Let's look at what happens if the pilot now reduces power. At the lower power setting, propeller thrust decreases. If the pilot holds his altitude by raising the nose a little to increase angle of attack, drag will exceed thrust and the aircraft will slow down. The deceleration continues until the drag has reduced to the extent that it, once again, exactly opposes the thrust, at which point the aircraft maintains its new lower speed. The lift still balances the weight because of the increased angle of attack, and thus the aircraft maintains level flight at the lower speed. If, however, the pilot wishes to maintain 100 knots at the reduced power setting, he must select a more nose-down attitude. The magnitude and distribution of forces now cause the aircraft to descend. As you see on screen, a component of the aircraft's weight now acts in the direction of the aircraft's flight path, which, added to the remaining thrust from the propeller, balances the original drag. The aircraft will thus maintain 100 knots while descending at a certain constant angle of descent. The component of weight acting along the aircraft's new descending flight path is sometimes referred to as weight apparent thrust. If thrust were reduced even more, then more weight apparent thrust is needed to balance drag and maintain the speed. Thus the nose must be lowered even more, which will increase both angle and rate of descent. If power were now increased, propeller thrust would likewise increase. If the same nose-down attitude were held, the combination of the greater propeller thrust and the weight apparent thrust would exceed drag, and the aircraft would accelerate. We can see then that if the pilot wishes to maintain 100 knots, less weight apparent thrust is required to balance the drag. Consequently, to maintain speed, the nose is raised. The sum of propeller thrust and weight apparent thrust is again balanced by drag, and the aircraft descends at a shallower descent angle and lower rate of descent. From the preceding examination, the important interrelationship between airspeed, propeller thrust, angle and rate of descent should now be clear. If airspeed is to be kept constant as power, that is, propeller thrust, is decreased or increased, the pitch attitude of the aircraft must be varied accordingly. For example, either by lowering the nose as shown here to maintain 100 knots if power is reduced, or by raising the nose, as you see on the screen now, to maintain 100 knots if power is increased. Similarly, if the pilot wishes to control his angle or rate of descent while maintaining constant airspeed, he does so by increasing or reducing power, and thereby propeller thrust. As we've learned, Adjustments in power and changes in pitch attitude to maintain speed will also modify the rate and angle of descent. For example, if an aircraft is descending at an airspeed of 100 knots and at a given power setting, reducing power will increase the angle and rate of descent as the pilot adjusts the aircraft's pitch attitude to maintain 100 knots, while increasing power will reduce angle and rate of descent as the pilot again adjusts pitch attitude to maintain 100 knots. This teaching point must be thoroughly learnt if you are to fly a successful approach and landing in a propeller-driven light aircraft. To summarize, we may say that power setting, speed, angle of descent and rate of descent are all inextricably interrelated. A change in any one of these factors will produce changes in the other three. If power is reduced to a minimum by closing the throttle and the aircraft is trimmed to maintain a given speed, the aircraft is said to be gliding. This simple form of descent is used in all forms of flying and will play an important part in your flying training. In a true glide, there is no thrust from the propeller. In an actual glide descent, though, although your throttle is closed, you will readily appreciate that, with the engine at idle power, a small residual thrust force from the propeller does remain. For this explanation, however, we will assume zero thrust. Assuming zero thrust, then, as you see on screen, the only forces acting on the aircraft in a glide are lift, drag, and weight. In a steady glide at a constant airspeed, these three forces are in equilibrium, with the weight being balanced by the resultant of lift and drag forces, depicted as RLD on screen. In this situation, the force propelling the aircraft forward is the force of gravity, or more precisely, a component of the aircraft's weight acting in the direction of its glide path. This propulsive force is known as weight apparent thrust. In a steady glide at constant airspeed, weight apparent thrust will be equal and opposite to the drag. If we slightly modify our vector diagram of the flight forces acting in the glide, and look at the bigger picture which shows the aircraft's glide angle with respect to the ground, assuming no wind, it's easy to prove geometrically that the angle formed between the lift vector and the resultant of the lift and drag vectors, RLD, is the same as the angle between the aircraft's glide path and the ground. Here the glide angle is depicted by theta. It's clear that the smaller the angle theta, the shallower will be the aircraft's glide angle, and consequently the better will be the aircraft's gliding range. Theta becomes smaller as the ratio of lift to drag, normally referred to as the lift-drag ratio, gets higher. The pilot has no instrument to indicate to him when he's flying at the best lift-drag ratio for his aircraft. But, as you'll have learned in your ground school studies, the lift-drag ratio is a function of the angle of attack. As we see on screen, there is a value for the angle of attack which will give the best lift-drag ratio. For most light aircraft wing sections, this is about 4 degrees. You will also have learnt that in a glide, as in level flight, there is a direct relationship between airspeed and angle of attack. As airspeed increases, angle of attack decreases, and vice versa. It follows, then, that there is also a direct relationship between the lift-drag ratio and airspeed, and that consequently a speed can be determined for your aircraft which gives the flattest gliding angle, that is, the best gliding range. This speed will be found in the pilot's operating handbook. For the Warrior, that speed is 75 knots, giving a maximum lift-drag ratio in the order of 10 to 1, and a best glide angle of about 7 degrees. In practice, of course, a pilot would want to remember this information in the form of his aircraft's best glide performance. That's to say that in still air a Warrior would glide some 5 nautical miles from 3,000 feet at an airspeed of 75 knots. If you look in your pilot's operating handbook, you'll notice that the best glide speed is very close to the speed which gives maximum range, because the lift-drag ratio is an expression of the aerodynamic efficiency of the aircraft. So, at the best lift-drag ratio, the aircraft is operating at maximum efficiency. Knowing that the lift-drag ratio is a measure of the gliding efficiency of an aircraft, it follows that any factor affecting the lift-drag ratio will affect the gliding performance. We've already learned that speed is one of these factors. The other major factor is the use of flap, which, as you're taught in ground school and in the effects of controls lesson, modifies the relationship between the lift and drag forces. We'll consider each of these factors in turn. As we've just seen, for all aircraft there is an airspeed for maximum lift-drag ratio and maximum gliding range. If the pilot glides at a speed other than this best glide speed, his aircraft's glide angle will be steeper and its glide range shorter. So, flying faster than the best glide speed will decrease gliding range. And flying slower than best glide speed will also decrease gliding range. It is most important, both from the airmanship and the flight safety point of view, that you fully appreciate the implications of gliding at speeds above and below the best gliding speed, especially at speeds below the best glide speed. Let's look at the situation a little more closely. We know then that there is a best glide speed at which an aircraft achieves its best glide performance. That is, at this speed it covers the maximum horizontal distance for minimum loss of height. In the Warrior, that speed is 75 knots. We know too that flying faster or slower than best glide speed will make our glide angle steeper, or, in other words, will lower our glide performance. When we are flying more slowly than the best glide speed, our nose is pitched relatively high. This is a particularly dangerous situation, because the pilot, from his perspective looking forward out of the cockpit, may get the impression from the nose-high attitude that the aircraft is gliding in the direction in which the nose is pointing, and that its gliding angle is shallow. As we now know, this is a totally false impression. So, how can a pilot measure the glide performance that his aircraft is achieving? This is relatively straightforward.